I think this is a good time. So thanks everyone for coming. We have a very exciting talk today by Krzysztof Geras from NYU talking about how to solve breast cancer diagnosis with deep learning and all of the challenges and opportunities in developing these models. We, from the advertisement, we've seen that you can't use out of the box convolutional neural networks at all times. There's a lot of other model development challenges and other challenges that are required to do it well. And Krzysztof has been tackling this for many years. So we're excited to hear his insights into what needs to be done to get really good performance with low false positive rates and false negative rates. Where we will hear from leaders in the field and discuss general trends in AI for healthcare. And our goal is to bring together AI researchers in a variety of fields. So we're highly interdisciplinary, spanning computer science, engineering, but also epidemiology, radiology, nutrition, and bringing together scientists, but also clinicians and also advocates. So we want to bring everyone together to hear from the experts and to discuss what the next steps of the field should be. So the format of this is roughly a 30 to 40-minute talk, and it's very rough. It can be longer or shorter, and then an interactive question and answer session. And if you have any feedback or speaker suggestions, please send them to John and or me. We are hosted by the UH Cancer Center, the Hawaii Data Science Institute, the AI PHI, and so we're really excited to host this. We also like to do a paper of the month, and I thought a nice paper of the month, which came out just in 2022 from Science Translational Medicine from Krzysztof's lab on improving breast cancer diagnostics with deep learning for MRI, which I assume we'll hear about some of the work in here today. But Krzysztof has published, interestingly, in both the top medical journals, but also the top CS conferences like ICML. So he truly does span both areas well. And so we're really excited to hear his insights. We also have a speaker compensation for all of our speakers, a beer stein branded with the AI PHI logo. So Krzysztof, you should be receiving that very soon. So without further ado, I will let you share your screen, Krzysztof, and thanks so much for coming.
Sure. Okay, so let me share my screen and we can start. Okay. All right. Okay, so actually, funnily enough, I think the paper that's that you mentioned, I really like that paper. But actually, I think it is it's a very well executed study. But I think it's I think it's kind of building upon many of the ideas that we have that we have used in the past. But actually, I think there are other works that's where we have done kind of more innovative, where we have developed more innovative technologies that kind of went slightly unnoticed. But yeah, so maybe getting back to why I'm here today. Basically, I think the format of my talk is that I will just try to give you some insight into what I went through in the last 6-7 years to develop these models. I have some slides, but I think my slides are fairly, I wouldn't, basically I'm very happy to answer the questions during the slides, and I don't come with some kind of, let's say, I'm very happy to even not to talk about everything I have on my slides, but actually to focus on some elements that are more interesting to you. And I'm also very happy to go deeper into certain aspects if they are if you find them interesting. Okay, so maybe to begin with, I would like to argue that deep learning really is the right tool for medical image analysis, and I think it is somewhat clear now. But I think it hasn't been clear for very many people until relatively recently. You know, but it is the right tool for this very basic reason that is on the right part of this chart, right? So we can think of basically all learning tasks as being on this 2D plane, right? Where the x axis is the difficulty of the task and the y-axis is the number of available data. And in this bottom left corner, you know, we have those learning tasks for which we don't have very much data, but are also relatively simple. So, you know, like a classic example of this would be something like iris classification. Probably everybody has, tried in their very first machine learning exercise. Here, you know, if you have a decision tree, you can solve it to a very high degree of quality. Very often you can't solve it perfectly, not because you don't have the right method, but maybe because of the noise in the labels. But classic machine learning methods are completely sufficient there. Then, if you have easy tasks and a lot of data, I mean, it's not interesting because you can already solve them with with smaller number of data. If you have a very difficult task, but you have very little data, then practically you cannot do anything. So it is also not very interesting because you just, whatever you do, you're just never going to be able to solve this without, you know, some incredibly strong inductive bias coming from either modeling or for example, transfer learning, right? Basically, these are the tasks that are not particularly, I mean, usually basically just you cannot do anything in them. And then there is a corner of that. There is a corner on this chart where you have a lot of data and for difficult tasks. And this is really where deep learning is very useful because it has the power to model very complex phenomena in the data, while at the same time has very good generalization properties. And and I think, okay, so this is an argument that should convince you, but also experimentally, there were plenty of successes already in medical imaging with deep learning methods. You know, whether this is ophthalmology, pathology, radiology of different kinds, and dermatology, right? I think at this point it's pretty well established that deep learning really is the way to go with medical data, and I think nobody would really question this these days. And in particular, in my talk, I'm just going to give you a small snapshot of those different opportunities by describing my experience with working with breast cancer data. So why is breast cancer even important? Well, it's primarily important because it's a very common cancer. And going back to my previous slide, there's a lot of data. So there's actually about 40 million cancer screening exams performed in the US. 40 million only in the US performed every year. And there's actually a lot of women who are diagnosed with cancer. And breast cancer is relatively deadly. Actually, about 40,000 women lose their lives to cancer. So it is a very good task for machine learning because we have data to solve it, and it's an important problem, right? So even if we make a relatively small progress in it, then there's a potential to impact the lives of very many people. And as you may probably know, in most places, breast cancer screening is implemented by taking those 4 images of the breast, because a healthy woman typically has 2 breasts, and there are 2 views of the breast. right? So the views of the breast, so the MLO view and the CC view indicate the kind of an angle at which the breasts are squeezed. So this is what I'm showing you is called full field digital mammography. There are also slightly more modern versions of that now, which is called digital breast tomosynthesis. I'm going to just, I'm going to present some of these ideas for full field digital mammography, but also many of them we later applied to DBT. Okay, so where does this actually fit in this full imaging workflow for breasts, right? So as the name suggests, screening mammography happens at the very beginning of this workflow. If there is a healthy asymptomatic woman, they come for a regular yearly exam. And, the good outcome is if doctor says, this is certainly a healthy patient, there is no need for further imaging. However, if there is a possibility that this woman has cancer, then we don't go straight to a biopsy, but there are some intermediate modalities to exclude the possibility of cancer. So there's an ultrasound or diagnostic mammography. Sometimes they are done, well, depending on women, one or the other is preferred. Sometimes they get both. If these imaging modalities still don't exclude cancer, then typically the next step is MRI. And if the cancer still can't be excluded, then then there is no other way to conclude whether this person is healthy or not, except for pathology, right? So the pathology is, so basically pathology consists of putting a small metal tube into somebody's body. Well, that's a biopsy, right? So a small metal tube is put into somebody's body, a piece of tissue is taken out, and then someone looks at the microscope, and then there can be a conclusion whether this person is healthy or not. And essentially, what we would like to do ideally is to take the input of screening mammography and to be able to obviate the need for these intermediate imaging procedures, right? So what we would like to do is we would like to take that take the screening mammography and just conclude with high confidence that there is no cancer, or otherwise, if we predict that there is a benign or malignant change, then there still will be those procedures will still have to be conducted, but we're just hoping that in an overwhelming majority of cases, we'll be able to say this person is healthy and there's no need to do anything. And therefore, we could possibly save a lot of anxiety for the patients and also a lot of money for the hospital system. Okay, so but basically, how do we frame it as a learning task? We say that we have these 4 images as input. We throw this into a learning model. In our case, this is a neural network, and then we make a prediction for whether in either of the breasts there is a malignant lesion or there is a benign lesion. Although we are not really interested in identifying benign lesions that much, it is useful to also use the benign lesions as a target in that procedure, because it regularizes the learning. So this is an instance of something which is commonly known as multitask learning. Okay, but now I think we all agree that it's easy to download PyTorch from the internet, and everybody can basically train neural networks, right? Like you don't need to be any kind of a massive expert in machine learning to actually train neural nets. So why is this why is this even hard, right? Like why do I need to work at the university and I'm even giving talks about this stuff? Well, because it's not as easy as it seems. So first, it is, a very important operational problem of doing any kind of meaningful research in medical image analysis, is that there are relatively few public data sets of high quality. So while there's a lot of great data sets of natural images, for example, ImageNet, still, even I think even now the only really public data set of mammograms is only 10,000 images. There now exist somehow semi-public data sets which are bigger, but but they require other types of, they require some agreements rather than, they're not just freely available to download from the internet for everybody. So, so to do any of this research, we had to actually collect data from our hospital system. And, in this initial version of the data sets, so this is our original data set from 2017. In that data set, we actually had 1 million images. Now I think we like this, well, we have about 5 times more images that we are working with. Okay, so first, this is a really important struggle for for researchers that are not connected necessarily to a large hospital system. And then the other thing is that there is a more fundamental issue with medical images, and I think a lot of the differences in how neural networks for medical images should be different from neural networks for for like making classifications in something like ImageNet comes from what I'm about to demonstrate. So if you look at the bottom left corner, you will see something there. And can someone tell me what that is? It's a part of an exercise. Yes, it is a panda indeed, right? And so we take this so the natural images can be subsampled insanely without the loss of information that's necessary for classification, right? So the subsampled image is actually maybe 1,000 times smaller than the full image, and yet you can still tell that this is a panda. And that's because in natural images, the prediction of the class of the image is typically made based on some features that span a large fraction of the image. And that is just not the case in most medical images. It's the opposite, right? So there's a very small picture of a very small breast mammogram, very small mammogram, right? Like you cannot tell whether this person is healthy or not. And even the full scale image, most radiologists would decline to make a prediction with, because they would say that this is not a diagnostic, this is a wrong screen. They basically need a very particular environment in which they are actually comfortable in making these predictions. And that is because very often the objects that determine whether this is a healthy person or whether this person has cancer are actually extremely tiny. So we cannot apply the same trick as we do with natural images. We cannot just take this huge image, make it very small, and then just train a regular neural net, right? So we just have to accept that those images are huge, and we have to accept all of the consequences coming with that, right? So that we have to adjust our neural network architectures to deal with these massive images, and therefore we have to modify them such that they can the memory in those neural networks can be managed to still work effectively. So in summary, the public data sets are very tiny and the hospitals are really not very keen to share data, even between themselves. In addition, actually labeling medical data on pixel level is difficult, and it is difficult both operationally, because there is a small number of people that can perform this kind of labeling accurately, and you have to put them in front of a computer for many hours to obtain this data set, and it's also difficult. Well, it's also difficult objectively, because just sometimes it is just based on the image, it's difficult to say where the cancer begins and where it ends. So there's some inherent uncertainty in the annotations we are collecting. And then what I've illustrated in the previous few slides, medical images are actually they have very different properties than standard neural networks and the standard natural images, and therefore we have to design different kinds of neural networks for these images. And also the standard neural network architectures that everybody's works with on a regular basis just don't have any direct mechanism to explain their predictions. And it is possible to, of course, obtain these kind of explanations post hoc, but as I'm going to show you in a minute, it's actually better to actually make the explanation a part of the prediction. Yeah, and also I think somewhat philosophically, it's difficult to evaluate the impact of machine learning in medicine, because to be very certain that that we have actually made an impact, typically we need some kind of a prospective study, and that could take years to be conducted, and then the data from this prospective study to be evaluated. So it is not, it is just much harder than in many other applications of machine learning. Okay, so now I'm going to show you one idea of how we solve some of these problems, just as an illustration. We call this neural network globally aware multiple instance classifier, and I'm going to unpack this image for you step by step. Okay, so in the first step, what we did is we have created something which we call a global module, which is essentially a neural network similar to a ResNet. However, it would be typically a fairly shallow ResNet, so that we can feasibly store its internal space in the memory of a GPU. And the other modification that we have done is that it is using a special layer. So it is not so a typical neural network wouldn't have the sigmoid layer, it wouldn't have this convolutional layer, and it wouldn't have the saliency map. Basically, it wouldn't have these. A typical ResNet basically has some number of convolutional layers, right? And then it has a global average pooling, and then this globally averaged pool representation is used to make classification. And what we are doing here is actually something quite different, right? So what we are doing is we are actually taking those convolutional representations, and we are squeezing those representations through to only two feature maps with a 1-by-1 convolutional layer and a sigmoid layer applied as a nonlinearity. And therefore, we are pushing, basically what we are obtaining is what we call two saliency maps that we can project back at the original input image. And what we are hoping is that the saliency map indicates the locations of the objects that indicate the class, right? So And then to obtain the class prediction, we do global average pooling, and then we, and that is our prediction, right? But through this, through this trick of creating these saliency maps that is exploiting some properties of the neural networks, of the convolutional neural networks, we're essentially obtaining an explanation as a part of the architecture. So we have this, okay, so what we have is a prediction based on this low capacity network, and then we have this explanation in the form of the saliency maps that indicate those bits of the image that indicate the class. In our case, it will be either benign lesions or malignant lesions. Of course, now, because this is a relatively low capacity network, it won't be correct every time. So what we have to do is we have to then look at these saliency maps. We have to extract a number of patches, and then we can look at them with some higher capacity network. And that is, a more standard ResNet with a larger number of layers. From each of these patches, we get a feature vector. We can use the attention mechanism to form an attention-weighted representation, and then again create a prediction based on this collection of patches. And then we have, and then finally we have. We can also take the representation from those formed by this attention-weighted representation for the patches. We can take the representation from the global network. We can concatenate it, and then we can have some representation that takes into account both. Yeah. Okay. So I think this is one way of doing that. Obviously, there are other designs that would work similarly, but this one works very well. The big advantage of this design is that it's actually incredibly simple to train. Basically, all that we do is we just without even any weighting, we train these three optimization objectives, and we add a little bit of regularization to the saliency map. So this regularizer is just L1. It's an L1 loss so that the saliency maps are just they are sparser, right? So we don't have these kind of values that are just near zero, but if they're close to zero, then they get shrunk to zero. So this is how we get these contiguous regions like here.
Hey, Krzysztof, I have a couple questions on the architecture. First of all, why do you have two saliency maps?
Oh, because we make predictions. Yeah, so because we make predictions for benign and malignant lesions. So one corresponds to benign lesions, one corresponds to malignant lesions. But yeah, we could have just one. If we just only wanted to detect, if we only wanted to identify malignant lesions, yeah.
And then my other question was, do you train these models separately? Like, can you train each one independently and then plug them together, or do you train all of them from scratch?
I think you could train them one after the other, right? So you could probably train this one first, then this one, and then this one. But we just trained them all together because it was the simplest thing to do, and it works very well. I mean, obviously, if that didn't work, then we would assume that it's a harder optimization, and we would probably have tried training them separately and then training them together, but it just wasn't necessary.
Great, thanks.
Okay. Yeah, and it actually works, right? So I mean, this is just one example, but this is annotated input, right? And well, like those are the patches that this neural network found, and these are the saliency maps. What you're going to notice is that the saliency map indicating benign lesions and malignant lesions are both activated at this location, and that's for a good reason. It's just very often it's just the benign lesions and malignant lesions are just indistinguishable, right? I mean, it's just a limitation of the of mammography, right? You just cannot hope to completely overcome this with neural networks. But it correctly identifies the lesion that actually was later biopsied, even though this annotation was never part of the training, which is like, that's the important part, right? So it has this annotation map was discovered by the neural network trained only with image level labels. Okay, I mean, I won't go very deep into this, but this is just to convince you that this was working very well, right? So, well, basically, this is, this AUC is a number between 0 and 1, where 1 indicates the perfect prediction, and our ensemble of these GMIC ResNets, we got 0.93 AUC, which in our experiments was actually higher than faster AUC, faster RCNN that actually is trained with the bounding boxes as well. Okay, and it's very computationally efficient. You can even find cancer in some cases that radiologists consider mammographically occult. That's an example of that phenomenon. So this is an image from a woman that came for a screening mammogram. The radiologist said that it is somewhat suspicious because there are these dense tissues, but they don't actually know whether there is any cancer there or not. So they asked them to do an ultrasound. And the ultrasound confirmed that this person actually does indeed have cancer, while our model was actually capable of indicating the location of that cancer without the ultrasound, right? So we retrospectively, basically we run it retrospectively, right? So we asked the radiologist to confirm with the report that that's actually indeed the location that where this ultrasound image was taken. And yeah, so I think this is just a very interesting case, how a neural network can not just learn to mimic a human, but it can, but through this mechanism of making an explanation part of the model, it can actually even discover something on its own. I think that's a very interesting direction in general. Okay, and in the human performance, we have a reader study where we have 720 exams. We had 7 attending radiologists, and we asked them for a prediction of probability of malignancy. We only asked them to, well, we are comparing in terms of predicting the malignant lesions, right? Because predicting the benign lesions isn't that interesting in that setting. And what we found is that, I mean, it's in the paper, but so I won't go into great details in this, but in the comment of 2 common ways of evaluating neural networks in this context, the AUC curve and the ROC curve and the precision recall curve. We have been able to show that if we take the predictions of the radiologists and we average them with the predictions of the neural network, then all of these radiologists go up in their performance, right? So, basically, all of these curves for all of radiologists go up, and the average, obviously, is also higher. And you can download this from the internet. It is available at GitHub. Both the weights and the model. Basically, you can do whatever you want with that, just as long as you stick to the AGPL license. So which means that you have to release your code on the same license. And we also, because we realized that it is difficult to compare these models, we have also created a meta repository of the models. where you can pick you can pick a data set and you can pick a model from a collection of models that we found on the internet and our own models, and it enables very easy comparison between different models. So I also encourage you to look at that. And of course, like I mentioned before, these days, digital breast tomosynthesis is it's already a more popular imaging modality, and it's going to dominate FFDM eventually. So we also applied similar ideas to 3D, and it also works very well. So you can see, so you can see that as we look at this, the different slides of the DBT show up, and also here, here also this a very similar model works very well. And also you can apply the same ideas to, or very similar ideas to breast ultrasounds. We also have a paper about this. Here, we are creating an attention-weighted representation among different images that are part of the ultrasound exam. And we can compute importance of different image scores, and we apply this to different scores for different images. And so basically we have essentially three outcomes of this. So we have the image level scores, we have the pixel level scores for each image, and then we have the breast level prediction. And yeah, experimentally, we were also able to show that this is very effective. Here, we were able to, in terms of the ROC curve, we were able either to beat or to draw all radiologists that participated in the reader study. There was one real champion radiologist. There is one real champion radiologist at NYU who is always beating all other radiologists in all other studies. And like this radiology champ, like we were not able to beat her, but she's really amazing. So but it's the same here, but it's the same in terms of the precision recall curve. We were only one radiologist. We were not able to either beat or draw. And in terms of, we actually, again, we looked at how our AI corresponds to the performance of the radiologists individually and the hybrids between radiologists and AI. And as you can see, we were able to improve the performance by averaging the prediction of radiologists with the AI. We were able to improve performance of all radiologists in terms of AUC, AUPRC. We're capable of increasing their specificity. We're able to decrease their biopsy rate and increase their positive predictive value. So, okay, basically what we computed, I mean, the summary of this is that we computed specificity and sensitivity for radiologists. And then we looked at AI specificity at radiologist sensitivity, and it was higher than radiologists. And we also looked at AI sensitivity and radiologist specificity, and that we also were able to improve these numbers. Okay, but now, where do I see this actually going forward? I think we should, on a high level, I think we should go beyond this paradigm that AI can only support radiologists in existing tasks. I think it's very limiting to think about it this way, because, well, primarily because, humans, human brains and neural networks don't work necessarily in the same way. And there is such a great wealth of tasks that are just completely implausible for humans, while they are potentially relatively easy for neural networks. So let me just give you an example, some examples of what I mean by this. Okay, so this is what radiologists essentially do, right? They look at the images, let's say we are in the year 2021, and they look at those images and they make a prediction for whether this person has cancer, right? That's essentially what they do. Now, there's nothing stopping us from asking the neural network whether this person will develop cancer in 2023 or maybe 2026. While this is, while this is totally inconceivable for a radiologist to make this prediction accurately, a neural network has a much larger capacity to develop some high frequency patterns in the data, such that these kind of predictions are actually, actually plausible. And you have, and there are people, I know that there already are people actually working in these directions, and and these kind of networks work reasonably well already. Furthermore, we can actually very effectively compare the predictions from, we can very effectively compare the images from the current year to the images from the prior years. And while radiologists do this themselves to a certain degree, we can do this much more efficiently using neural networks. And and we can very efficiently discard very many potentially suspicious lesions just because they exist in the prior images and they are stable. And maybe even more importantly, something that I'm personally actually working very hard on right now is making sense of those multimodal predictions, right? So it is very limiting to think about one type of imaging at a time when we actually have so many different types of images. So we have, we have the screening mammograms, we have the diagnostic mammograms, we have the ultrasound, and we have the MRI. So why not just take them all together, put them into some kind of a network that can reason about the different elements in these images, and then make a prediction jointly based on these. So I could just tell you that, well, it's the paper that we have on this is not yet published, but I can tell you that it's already, that is working very well. And, based on this kind of, furthermore, building on the kind of representations that you can build from multimodal data, you can actually answer a lot more interesting questions. So for example, not just whether this person has cancer, but maybe what type of cancer this person has. Or, or if this person does have cancer, what is going to be their response to some kind of a therapy? There's just so many different things that we could use based on this data than we are currently doing. A topic that I also think is very underexplored in machine learning and in application to medical imaging is actually optimizing the workflow of how the different images are acquired. So this is what I'm showing you on the screen is a very, this is a somewhat simplified imaging workflow for a person who's coming to, so I specifically extracted this from my colleagues at NYU. But there are very many different paths a patient can take. And all of these different paths are somewhat based on a mixture of existing guidelines, experience, availability of the imaging resources, etc., etc. Right? So the same patient can actually have a very different path here depending on some random factors. So this presents a perfect opportunity for AI to actually optimize this. And I think this is, this is not just in breast imaging, but in very many different applications of imaging. I think there is a lot of, there's a really potentially a huge impact of optimizing these, especially, as all of these procedures are very expensive. And, for some people, actually, some certain procedures are more appropriate than the others. So there's a huge cost that can be saved if we do this well. We also currently very limited in the research that we have done on the human AI interaction. In the results that I've been showing you, we were just averaging predictions of the AI with the predictions of radiologists. But this is a very cartoonish way of, introducing their interaction. Right? There's a possibility of very many different scenarios, right? So even, whether we use the AI as a second reader, or whether we use the AI as an aid during the reading time, or whether we use the AI or as some kind of a controller that maybe is looking at a certain fraction of the cases which are either very high or very low, right? So if they are very high on the list, then maybe even the radiologist even thought that this person is healthy. Maybe AI should override the person's prediction. Or if the AI thinks that some case is clearly normal, and the radiologist still decided to recall, maybe we should actually ignore. Maybe we should actually override a radiologist's recommendation, right? So there's a lot of questions about how these two should interact. And I think this question also goes beyond just machine learning. It's a more of a question of psychology and human-computer interaction. And I personally expect that there is going to be a lot of research in this direction in the coming years, and I think it's actually fascinating and very underexplored. A different direction that I am a strong believer in is that we should start discovering knowledge through machine learning, especially in medicine. What do I mean by this? Well, so if anybody who has ever learned machine learning knows this kind of a pattern, that if you are presented with a new machine learning problem, you are supposed to read some literature on the domain or talk to the domain expert, and then this expertise that you acquire through yourself or from someone else will lead you to design a network that's appropriate for that particular task. And that obviously is not a crazy way of thinking about it. However, these days we are actually training these neural networks on the amount of data that no human will ever be able to look at, right? So there's no chance that a human radiologist is going to analyze 5 million imaging exams, right? There's just no chance. There's just not enough time in our lifetime to do this. So I think the direction that I really would like to make work is that we should be able to actually train the neural networks with these massive data sets, and then be able to squeeze some knowledge out of these neural networks that would become some kind of scientific, that would then be would be some kind of scientific knowledge. Okay, so in conclusion, deep learning really is the right tool for medical image analysis. I think it's, at this point, I think it is without a doubt. A lot of progress has already been made. The neural networks such as the GMIC, which I presented, will definitely be used a lot in the future, because they are efficient. They can learn from on the image level labels, and they produce explanations natively as the part of their training and inference. But there's a lot of exciting room. There's a lot of room for exciting work, especially for 3D and multimodal data. AI is actually already superhuman in many medical image interpretation tasks, and that effect is going to become more and more apparent to everybody in the next few years. I think it's I think this is something that people begin to realize, but have a hard time accepting. But this is going to be obvious. You know, if you invite me in 5 years to give, you know, to give a talk, I'm very sure that nobody is going to. There's not going to be this kind of a conversation. You know, like, can AI detect things in images better than a human? It's going to be very obviously in favor of the, you know, in favor of the AI. Yeah, but we actually, you know, but it doesn't mean that, you know, our work is done. We actually have to understand how to use these models and deploy them in a safe way, such that it benefits the users. Okay, so I have, obviously, this kind of research cannot be done by one person. It's actually, you know, a large team of students and collaborators that led to execution of this work. I'm only showing here, actually, I'm showing here a subset. There's plenty more that I don't have here. Yeah, so thank you very much, and I am happy to answer any questions.
That's great. Thank you so much, Krzysztof. Let's open it up. It's too bad we can't applause because, you know, I always feel like on Zoom calls you can't really applaud. It's a really fantastic talk.
Thank you.
I have a lot of questions, but let's open it up to the floor to see who has some questions for Krzysztof. It's a great opportunity while we have him. One of the things that came up, and I was thinking about that you said about that super radiologist,
Right.
and those guys exist, and they're fantastic. And what always comes to mind when I think about people like that is that their lifetime is limited, and they're not going to be with us forever. And we've spent a lot of time and effort training that person, and when they're not with us anymore, that's gone. So, you know, your AI program, once it's trained, can be, you know, copied and multiplied and basically live forever, right?
Yes.
So but it's become a problem in lots of the areas I work in, and that you get these great algorithms, but the way that you try to implement them, it really goes against the standard, I guess, the clinical pay structure. And for example, in one field I work in bone, they have a great algorithm for looking at fracture risk from CT exams, and it can run automatically with no interaction and come up with a wonderful prediction that everybody likes. But they want to put that into a standard paradigm, which means that you need to have a clinical indication to even run the algorithm. And every time they run it, they want to be paid. And it's not a small, like $1. It's significant, right? It's the reimbursement that you would get from a normal radiologist interaction for doing that reading. And it basically stymies the whole thing. You know, you would like to take these algorithms many times and run them opportunistically. For example, deploy your algorithm in a healthcare center that's never had AI and do a baseline and say, how many did we miss, and how many, what new information can we learn on our entire population? But just the cost structures are not really set up to do that. And have you put any thought into that, about how medicine can go more the way of kind of the ideal of open AI, where you put a lot of money into development, people are well compensated for their time and effort that they put into development, but the algorithms then become effectively a service to the to society instead of a big profit, you know, center. What are your thoughts on that?
Yeah, I agree with you. I mean, I have similar thoughts about this. You know, but I think, okay, so one thing is, so maybe let me give you, okay, so maybe let me give you like separate, like an answer on several layers. So approximately 2 years ago, I know some people in a large foundation that has several $1 billion of money that they want to invest over next years. And I was trying to convince them to allow me to create an institute worth, I think I proposed $30 million back then to basically just create this thing, to create these kind of, let's say, which we would call, like models that everybody can access for a variety of different kinds of types of data. That's, of course, I'm not the director of this institute, so this institute didn't, that proposal didn't go through. But I think that's the future of doing this. So there's definitely, so there's no reason for so many different small companies trying to create competing tools that do exactly, either exactly the same or very similar things. I think there's, basically there's either going to be at one point a government push, or there's going to be some kind of enough, momentum in the, either in charity or some private sector to create these kind of models that everybody can build on top of. I think to a certain degree it is already happening. For example, NVIDIA, I think, releases these kind of models that they call foundation models. So eventually I think this is going to, like, it has to go this way. Like, basically that's the natural evolution of, that's going to be natural evolution of many different fields, that someone is going to create this massive model that's going to basically be a great, they're going to be the foundation for building some kind of more specialized models, but using the representations learned by this massive model.
Yeah, when I go to the doctor and I have an exam, I would like to have any opportunistic algorithm run on it that is possible to give me as much information as I can every visit, and that's definitely not happening now.
I know, yeah.
Yeah.
That's yeah, but yeah, anyway, I think this is going the direction that you want, in my opinion.
Peter?
Yeah, so I feel like if you had a giant data set that was publicly available and anybody could train on, that might be just as good, right? Like, I think the data is kind of a bottleneck for a lot of these things. So can you say something about, the data set you have? Is that the biggest mammography data set in the world? And
I don't know.
is it like, do you have any thoughts on, like, federations, or who's the big players in building giant data sets?
I think my data set is probably not the biggest in the world right now. I think there are actually, I basically just at a certain point I concluded that building, my data set is big enough that I can do machine learning on it. And I didn't put that much effort into expanding the data set with data from other hospitals, etc. I think there is a data set created at Emory University, which is sort of semi-public, which is actually larger than my data set. So the semi-public, so the way it's semi-public is that I believe they allow everybody to access 20% of it after some kind of a vetting process. But, and I imagine that, if you collaborate with them, maybe they will let you access everything, right? But, but in this, for this kind of data, it's harder than other types of data, because those images are actually huge, right? So even though, one problem is that, like, I've been trying to release these kind of data sets for years, and I've been trying to approach this from different angles, and basically, like, every time I tried, I just found it so hard that I just was giving up, even though I was actually reasonably persistent. But there is just, but the hospital systems as such, they're not very keen on releasing these large data sets because there's lots of risks associated with releasing them. And, they're also thinking about it, especially, I don't know how that would be, maybe in Europe, there's a different line of thinking about it, but, in America, people are thinking about these data sets as, property of the hospital system that maybe they will want to make some money on in the future. So it's it's kind of very natural, right? I think probably all hospital systems think about it this way. But even if like it was possible to just, even if I could just today throw this data set into, out there, it is still, several hundred terabytes. How do I even, where do I even put this, right?
Right.
How do people even download that? Right? I don't know. I think there's no, I don't know of any, I don't know of any good way of doing this. Actually, there's, some people I know, for example, set up a server that they let you access if you have their permission, so there is a university in Sweden where you can, where basically you can ask, if you fulfill certain criteria, they will let you log into their computer and you can do some experiments on their data set through the interface they enable you to use, but they don't let you download things necessarily.
That's the Karolinska?
Yeah.
Mm-hmm. Well, I have another question. You're familiar with the paper that Carolina Freeman did that tried to compare performance across different AI models and for different situations, from either pre-selecting high-risk cases or being a second reader. And the interesting thing that she found was that most of the studies really didn't pass the criteria of being high-quality studies.
Okay.
Do you know the paper I'm talking about? It was just 2 years ago. Oh, okay. So I was wondering if you were familiar with that, because it provided a guide for study design for AI, and to make sure there was least bias as possible.
Mm-hmm.
And in your data set, do you have a pretty good, do you keep up or even know of things like race and ethnicity? Is that a variable that you have access to for your mammography data set?
Yeah, so yeah, we control that. We have done some experiments. I'm not sure if they are in any papers, but yeah, we have, we have extracted these, and we checked whether our model performs consistently across different subgroups, and we found that there isn't there weren't any massive changes between different races. I think what made a bigger difference was the density of the breast, because it's just obviously harder to see the cancer in the very dense breasts. But these models are generally fairly robust,
if they're trained on robust data, right?
Yeah, if the data is sufficiently, large and it's not subsampled in some uncontrollable way, then it is that these models are typically quite robust to this kind of selection of the subgroups.
Any other questions?
Yes, can I ask a question?
Yes.
Sure.
In your approach for the deep learning, are you following a large the LLM type of models with BERT or microBERT, and are you looking at generating confidence levels in your decisions? So you can integrate with the LLMs, you can integrate very large data sets. The problem is that as a university or small companies, those might not be affordable to kind of start pumping these terabytes or into the model. So that's one way, is that how are you following the LLM type of approaches for making the decision? And then when you're making the decision, are you looking at generating confidence levels or intervals or for risk or variances in the decision making? Thank you.
Sure. Okay, so you know what? I think okay, maybe I'll answer your second question first about generating, let's say, like indicating some kind of uncertainty about the prediction. So I'm not. The short answer is I'm not doing that right now, but this is something that I'm actually working on with a collaborator. Because,
Sure.
So in a way, uncertainty in a way can be decomposed, let's say, in some kind of inherent uncertainty of the data. So so the model is not very confident when it says there's like 70% chance of the cancer, but not 90. So you cannot do very much about that. But the useful, I think the useful thing that you could possibly do is when it gives you its prediction, you can estimate how confident it is that it about this particular prediction, right? So that's what I'm working on. In terms of large language models, I'm not sure if I fully understand your question, because language models don't make predictions on image data, but but they have some useful. They are useful, for example, I think in analyzing pathology reports, right, and asking, so that kind of thing I'm doing, yeah. But
there is a big move into the transformers, basically.
Oh,
and there's
right,
a big
right.
push on transformers where you're integrating, infusing multiple information
Right.
to do it. I mean,
I
that's
see your
basically
point.
what I'm kind of
I see your
going
point. Yes,
after.
yes. So yeah, so I am working in such directions as well. So I can tell you, okay, I can just maybe, these papers are not yet published, so like I mean, I cannot give you the full conclusions, but but the intermediate conclusions we have is that the vision transformers actually work reasonably well on this kind of images. You can train them to similar accuracy as convolutional neural networks, but there isn't a huge difference. I think what is the more interesting application of transformers is to train neural networks to make predictions based on a sequence of exams, for example, or incorporate some kind of side information into classification, right? So maybe if you could integrate, like patient history or something like this. Like it's somewhat awkward to integrate this kind of information into a convolutional neural network. And it's much more natural to do this in the context of, transformers.
Thank you.
I have another question. It has to do with quality control. So let's say, for example, your algorithm's implemented, it's being used in the field. Multiple different systems are seen to be as valid using retrospective data. And then there's a, how do you assure on an individual system that the algorithm stays in calibration for its accuracy over time, even though you might have changes in detectors, slight upgrades, algorithm changes on the pre-processing of the images? How do you do quality control with AI detection and classification algorithms in the field in a practical way?
Sure. So so I think the short answer is that I believe I'm not aware of anybody actually. I don't want to convince you about something untrue, but I am, at least I haven't seen such practical system that would actually do that with medical AI. However, there is there is this kind of a big idea which is called I think it's called Oh, I forgot what I forgot, but there's this kind of, there's this kind of like a big trend into thinking in this manner. I don't know, I don't think there is, like one single universal way of showing this, and ensuring that these models don't, don't go astray. I think it's more of a, some kind of collection of sanity checks, right? So for example, you could, like maybe one idea that you could apply is to, maybe like see whether the representations that you're learning from your neural network are not too different from the representations that you've learned on historical data, right? And do some kind of anomaly detection there.
Mm-hmm.
You could do a lot of, I imagine that you can do a lot of monitoring of the input, right? So for example, like low-level statistics of the inputs to make sure that they actually fit what your neural network was trained on. But but I think whatever you're going to come up with is going to be a collection of tricks rather than some kind of systematic solution, I believe. At least I don't know, I don't have like a I don't have like a, like another, I don't have an idea for like what exactly this new neural network to control the old neural network would look like.
Well, I don't know if you saw the paper at RSNA, but there was a presentation from someone in the UK that was had implemented an AI algorithm for controlling recall rates, and he monitored the recalls of patients in the rate over time, and it was 24 different centers, and they were averaging about 10%. Then something happened one at a time at each one of his centers where recall went up to 30%, and he couldn't figure out what it was until he did an investigation. And it turned out to be a software upgrade that the algorithm was not, dealing with very well. So it's a critical problem, and I think that it impedes the global implementation to have it be a stable solution in the field, because every 10 years or so, systems change technology. And I was interested. This is one more follow-up question. You mentioned how you applied your algorithms to single slices of the DBT. Did you retrain your full field algorithm for the single slices of the tomosynthesis, or did you find that it worked pretty well without retraining?
So it's neither.
Okay.
So it's a slightly different network.
Okay.
So it's a slightly different network, right? So it is basically looking at well, essentially it is looking at the entire DBT volume.
Okay, so it's a completely different algorithm. Okay.
I mean, it's not a completely different algorithm. It's an algorithm using similar ideas, right? It's similar. It's using similar ideas, but let's say this is not just an application of, like we didn't just like take the model trained on 2D mammography and we applied to DBT. It's a model trained from scratch.
Okay, I understand. We're running out of time, but is any other questions?
I had one more question about the ultrasound models you're working with.
Sure.
So we're very interested in the ultrasound models because, there's a lot of Pacific Islands that don't have access to mammography. And Ariana is a student, her microphone's down, but she was very interested in knowing whether you have plans to release some of the ultrasound models that you guys have built, since those are very interesting to us.
So it's a, I probably should not say very much about it when I'm recorded. but yeah, so like my honest intention is to always release everything we do, but it's I'm not in full control of how we release it, because I don't control it, right? I mean, basically I'm not an owner of these models. I mean, this is constantly on my mind to release those other models that we've created in the past, because we have some backlog of the models that we created and we haven't released. Okay, so maybe long story short is that if you email me, I think I might have a way now to share it with you. rather than sharing it publicly.
Great. Yeah, there's lots of things we'd like to follow up with you on
Sure.
as well. Peter, you want to close this out, or you want me to do it?
Yeah, I mean, thank you so much, Krzysztof. This was very educational and very inspiring, and lots of interesting ideas to talk about in the future. Explainable AI, multimodal, how do we fuse the two? And we should keep the conversations going. So let's give another round of applause to Krzysztof.
Thank you very much.
Have a great weekend.